Welcome to our comprehensive guide on the art of analyzing study conclusions in biomedical research. In today's world, biomedical studies are published at an unprecedented rate, and being able to critically evaluate their conclusions is more important than ever. Whether you're a student, healthcare professional, or simply interested in science, understanding how to interpret research findings can help you make informed decisions and contribute to meaningful discussion. In this video, we'll break down the key steps and concepts involved in analyzing study conclusions using real-world examples and practical tips. Let's begin our journey into the world of biomedical research analysis. Before diving into the technicalities, let's discuss why analyzing study conclusions is so crucial. Biomedical research directly impacts patient care, public health policies, and even our daily lives. Misinterpreting a study's findings can lead to misinformation, ineffective treatments, or wasted resources. By learning to critically assess conclusions, you empower yourself to separate robust evidence from weak claims. This skill not only benefits professionals but also helps the general public navigate the flood of health information encountered every day. Fundamental step in analyzing conclusions is understanding the study's design. Was it a randomized controlled trial, a cohort study, or a case control study? Each design has its strengths and limitations which influence the reliability of the conclusions. For example, randomized controlled trials are considered the gold standard for determining causality, while observational studies are more prone to bias. Knowing the type of study helps you interpret the results within the correct context and anticipate potential weaknesses. Next, consider the sample size and statistical power of the study. A small sample may not accurately represent the larger population, leading to unreliable conclusions. Statistical power refers to the study's ability to detect a true effect if one exists. Studies with low power are more likely to miss significant findings or report false positives. Always check if the sample size is justified and whether the study discusses its power calculation. Randomization and blinding are key features that reduce bias in biomedical studies. Randomization ensures that participants are assigned to groups by chance, minimizing selection bias. Blinding means that participants and sometimes researchers do not know which group received the intervention, reducing the risk of conscious or unconscious influence on the results. When analyzing conclusions, always look for these features and consider how their presence or absence might affect the study's validity. Control groups are essential for comparing the effects of an intervention against a baseline. A well-designed control group helps isolate the impact of the treatment and rules out alternative explanations for the results. When reviewing conclusions, ask whether the study included an appropriate control group and how it was managed. This can make a significant difference in the credibility of the findings. Outcome measures are the specific variables that researchers use to assess the effects of an intervention. These can include clinical outcomes, laboratory results, or patient-reported measures. It's important to determine whether the outcomes are clearly defined, relevant, and measured consistently. Vague or poorly chosen outcomes can weaken the study's conclusions and make it harder to apply the findings to real-world situations. Statistical significance is a common term in biomedical research, but it's often misunderstood. A statistically significant result means that the observed effect is unlikely to be due to chance, according to a predefined threshold, usually p0.05. However, statistical significance does not always imply clinical importance. When analyzing conclusions, consider both the statistical and practical significance of the finding. Beyond statistical significance, it's crucial to assess whether the study's findings are clinically relevant. Clinical relevance refers to the real-world impact of the results on patient care or health outcomes. Sometimes, a statistically significant result may have little practical value, while a non-significant result could still be meaningful in certain contexts. Always interpret conclusions with an eye toward their practical implication. Confounding variables are factors that can distort the relationship between the intervention and the outcome. For example, age, gender, or underlying health conditions might influence results independently of the treatment. Good studies identify and control for confounders through design or statistical methods. When reviewing conclusions, check whether the authors address potential confounding variables and how they manage them. Bias can creep into research at any stage, from study design to data interpretation. Common types include selection bias, measurement bias, and publication bias. Recognizing and minimizing bias is essential for drawing reliable conclusions. When analyzing a study, look for transparency in methodology and whether the authors discuss potential sources of bias and their mitigation strategies. Confidence intervals provide a range of values within which the true effect is likely to lie. A narrow confidence interval suggests precise estimates, while a wide interval indicates more uncertainty. When reviewing conclusions, pay attention to the width of the confidence intervals and whether they cross important thresholds such as no effect. This helps you gauge the reliability of the findings. Generalizability refers to how well the study's findings apply to populations beyond the study sample. Factors such as participant demographics, study setting, and inclusion criteria can affect generalizability. When analyzing conclusions, consider whether the results are relevant to your context or if there are limitations that restrict their broader application. One of the most common pitfalls in interpreting biomedical research is confusing correlation with causation. Just because two variables are associated does not mean one causes the other. Strong study designs, such as randomized controlled trials, are better suited for establishing causality. Always be cautious when drawing causal inferences from observational studies. Peer review is a critical process that helps ensure the quality and credibility of published research. However, not all peer-reviewed studies are flawless. It's important to consider the reputation of the journal, the transparency of the review process, and whether the study has been replicated. Peer review adds a layer of scrutiny, but your own critical analysis remains essential. Funding sources and conflicts of interest can influence study design, data interpretation, and reporting. Always check the disclosures section of a study to see who funded the research and whether the authors have any financial or personal interests that could bias the conclusions. Transparency in funding and conflicts of interest is a hallmark of trustworthy research. Single study rarely provides definitive answers. Replication, repeating a study's methods, and obtaining similar results strengthens the evidence for a conclusion. Consistency across multiple studies, especially in different populations and settings, increases confidence in the findings. When analyzing conclusions, look for references to replication and consistency in the literature. Systematic reviews and meta-analyses synthesize evidence from multiple studies, providing a higher level of confidence in the conclusions. These studies follow rigorous methods to minimize bias and offer a comprehensive overview of the available evidence. When possible, prioritize conclusions supported by systematic reviews or meta-analyses over those from single studies. No study is perfect, and every research project has limitations. These might include small sample sizes, short follow-up periods, or unmeasured confounders. Good studies openly discuss their limitations and how they might affect the conclusions. When analyzing research, pay close attention to the limitations section and consider how they impact the reliability and applicability of the findings. Transparency in research methods and data sharing allows others to verify findings and build upon previous work. Open access to protocols, raw data, and analysis code increases trust in the conclusions. When reviewing a study, check whether the authors provide access to their data and methods and whether the research is registered in a public database. Ethical considerations are fundamental in biomedical research. Studies involving human participants should have approval from an ethics committee and obtain informed consent. Ethical lapses can undermine the validity of the conclusions and harm participants. Always check for statements about ethical approval and participant consent when analyzing study conclusions. Negative results where no significant effect is found are just as important as positive findings. They help prevent publication bias and provide a more complete picture of the evidence. When analyzing conclusions, consider whether the study reports negative results transparently and discusses their implications for future research. Sometimes, study conclusions are overstated or hyped, especially in press releases or media coverage. Overinterpretation can mislead readers and distort the true significance of the findings. Always compare the study's actual results with the author's conclusions and be wary of exaggerated claims that go beyond the data. Subgroup analyses examine effects in specific groups within the study population, such as by age or gender. While these analyses can provide valuable insights, they also increase the risk of false positives due to multiple comparisons. When reviewing conclusions, check whether subgroup findings are pre-specified and interpreted with caution. When researchers test many hypotheses in a single study, the chance of finding a significant result by chance increases. This is known as the multiple comparisons problem. Good studies adjust for multiple testing using statistical methods. When analyzing conclusions, check whether the authors accounted for this issue. Effect size measures the magnitude of the difference or association found in a study. Unlike p-values, effect sizes provide information about the practical importance of the results. When reviewing conclusions, look for effect size estimates and consider whether they are clinically meaningful. P-hacking refers to manipulating data or analyses until statistically significant results are found. This practice can lead to misleading conclusions and undermines the credibility of the research. When analyzing a study, be alert for signs of p-hacking, such as selective reporting or unexplained changes in analysis methods. Pre-registration involves publicly documenting the study's methods and analysis plans before data collection begins. This practice helps prevent selective reporting and increases transparency. When reviewing conclusions, check whether the study was pre-registered and whether the analyses match the original plan. Open science movement advocates for greater transparency, data sharing, and reproducibility in research. Open science practices such as sharing data and code, pre-registering studies, and publishing in open access journals help improve the reliability of study conclusions. When analyzing research, look for evidence of open science practices. Guidelines and checklists such as CONSORT or PRISMA help standardize reporting and improve the quality of biomedical research. Studies that follow these guidelines are more likely to provide transparent and reliable conclusions. When reviewing research, check whether the authors mention adherence to relevant guidelines. Forest plots are graphical representations commonly used in meta-analyses to display the results of multiple studies. They show the effect size and confidence intervals for each study, as well as the overall summary estimate. Learning to interpret forest plots can help you quickly assess the consistency and strength of evidence across studies. Publication bias occurs when studies with positive or significant results are more likely to be published than those with negative or null findings. This can distort the evidence base and lead to overestimation of effects. When analyzing conclusions, consider whether publication bias might be present and look for efforts to address it, such as searching for unpublished studies. Expert consensus statements synthesize the best available evidence and expert opinion to provide guidance on clinical practice. While valuable, consensus statements are not infallible and should be interpreted in light of the underlying evidence. When analyzing conclusions, consider the strength and quality of the evidence supporting expert recommendations. Increasingly, patients are involved in designing and conducting biomedical research. Patient involvement can improve the relevance and applicability of study conclusions. When reviewing research, look for evidence of patient engagement and consider how it might influence the study's outcomes and interpretation. Advances in technology such as machine learning and big data analytics are transforming biomedical research. These tools can uncover patterns and relationships that might be missed by traditional methods. However, they also introduce new challenges such as data quality and algorithm transparency. When analyzing conclusions, consider how technology was used and whether its limitations are addressed. Reprints are research papers shared publicly before peer review. They allow rapid dissemination of findings but may not have undergone rigorous quality checks. When analyzing conclusions from preprints, exercise extra caution and look for subsequent peer-reviewed publications to confirm the findings. Supplementary materials often contain additional data, methods, or analyses that support the main findings. Reviewing these materials can provide a deeper understanding of the study and help verify the robustness of the conclusions. Always check for and review supplementary materials when available. Editorials and commentaries provide expert perspectives on new research findings. They can highlight strengths, weaknesses, and implications of a study's conclusions. While valuable, these pieces reflect the author's opinions and should be interpreted alongside the original research. Data visualization tools such as graphs and charts help communicate complex findings clearly. Effective visualizations can make it easier to interpret study conclusions, but misleading or poorly designed visuals can distort the message. Always critically evaluate the quality and accuracy of data visualizations in research. The language and framing used in study conclusions can influence interpretation. Words like may, suggests, or proves carry different levels of certainty. Be attentive to how conclusions are worded and whether the language accurately reflects the strength of the evidence. Reproducibility means that independent researchers can obtain the same results using the same methods and data. High reproducibility increases confidence in study conclusions. When analyzing research, look for evidence of reproducibility, such as detailed methods and open data. Negative controls are groups or conditions where no effect is expected. They help validate the study's methods and ensure that observed effects are not due to confounding factors. When reviewing conclusions, check whether negative controls were used and how they support the findings. Sensitivity analyses test how robust the study's conclusions are to changes in methods or assumptions. They help identify whether the results hold under different scenarios. When analyzing research, look for sensitivity analyses and consider how they affect your confidence in the conclusions. External validation involves testing the study's findings in independent datasets or populations. This process helps confirm that the conclusions are not specific to the original sample. When reviewing research, check for evidence of external validation to increase your confidence in the results. Summary: analyzing study conclusions in biomedical research is a multifaceted process that requires attention to study design, statistical methods, transparency, and practical relevance. By applying the principles discussed in this video, you can become a more critical consumer of scientific information and contribute to better decision-making in healthcare and beyond. Thank you for joining us on this journey to mastering the art of study analysis.